Hi, my name is Alexander Schindler, and this is our paper, Multi-Modal Video Forensic Platform for Investigating Post-Terrorist Attack Scenarios. The context of the paper is set to forensic investigation of video data after a terroristic attack. The objectives are to spot suspects, follow hints by civilian witnesses, collect and secure evidence, and to prevent immediate or subsequent attacks. I believe you all remember the attack on the Boston Marathon in 2013. Law enforcement agencies collected more than 5,000 hours of video data, which are 208 days or 7 months in total. It would take 13 person months or 2.5 person years to view and process this massive amount of data. The FBI had no tool assistance but relied on extensive personal resources, which were flown in from all over the USA. Because there is a considerable time pressure towards a timely content evaluation of mass video data, from media, politics, and the possible threat of a subsequent attack, the personal-intensive manual viewing process of the video footage is a suboptimal approach, and technical supporting tools were necessary. The presented demo paper is the outcome of 2 projects, Florida and Victoria, which created large-scale computing platforms for audiovisual analysis in the context of terroristic attacks.
So this is our web-based demonstrator. For the demo we have collected more than 10,000 YouTube videos from 7 different terrorist attack events. The video data is quite noisy. It contains raw footage from the events, as well as news coverage or propaganda. So the first step in our demonstrator, you select the case of the terrorist attack. Let's stay with the example of the Boston Marathon. The next step is to select the events or objects that you're looking for. In the case of the Boston Marathon attack, it was an attack with explosives, so we are looking for explosions. You can also specify a confidence value for the reliability of the prediction results. We can fine-grain the search by also selecting objects that have been identified by eyewitnesses, like cars or persons. And by pressing the search button we get a list of videos in which these events or objects have been detected, sorted by the confidence of the detection results. By clicking on one of the results you get a more detailed overview of the detection results. You can highlight the specific audio events and directly click into the waveform to jump to the right point of the detected event. In the video interface you see the detected objects. So in general this demonstrator integrates 4 analytic models: audio event detection, audio similarity retrieval, audio synchronization, and visual object detection and tracking. The use case is to provide a content filter in mass video data. For example, if the attack was a scenario with firearms, then identifying gunshots in media would provide a faster and easier entry point to an investigation. For the audio event detection model we are using recurrent convolutional neural networks with attention layer. The input representation consists of log-transformed MEL spectrograms. The attention layer is responsible for filtering non-relevant information from the input. This helps the network to learn faster and to converge better. It also helps for better generalization and at the end for a smoother prediction signal. The attention-filtered input signal is then processed by a stack of convolution layer which learn the latent audio representation. The sequence of audio embeddings is then processed by recurrent neural networks which learn the temporal dependencies between these embeddings. The output of the recurrent neural network is then connected to an array of fully connected layers, 1 layer per temporal dimension, and the dimensions of the layer represent the number of predefined classes that have to be detected. The output consists of weak labels in the training process and strong labels in inference. The model was trained on Google AudioSet, which is a collection of about 2 million videos, which have been annotated according to their acoustic categories and which is currently the largest source of audio data available. The dataset is not strongly but weakly labeled. Strong labels provide precise timestamps and durations for each class and label. Such datasets are very expensive to create and are usually small. Weak labels only provide classes that can be identified in a given time frame. In the case of the audio set, this time frame is 10 seconds. Weak labeling is very cheap, and so you can annotate larger datasets. We also didn't use the entire set of audio events provided by the audio set. because we retrieved suboptimal results from training on all events. So we first reduced the complexity of the taxonomy. We flattened and disentangled the hierarchy. For example, we used only parent labels for specific events. We also resolved ambiguities and overlaps. For example, we don't consider gunshots to be the same as artillery fire. We also removed non-project relevant labels like capgun or speech synthesizers. And we created a new grouping of classes. For example, artillery fire was moved to explosions, ambulance, police car, fire truck were merged together into the class of emergency vehicles. And then we created a selection of project relevant parent labels. We came up with gunshots, explosions, emergency vehicles, and so on. In a demonstrator, we are using waveforms of the audio data to visualize the temporal progression of the videos. Detected audio events are then highlighted in different colors. By this you get a better overview of the events that happen in the video, and you can directly jump into relevant segments of the video. But what happens if you spot a suspect in a certain video, but you cannot identify that person because it's looking away from the camera? The provided solution is that you select a range in the video and retrieve a list of similar sounding video segments. The implementation is based on a set of audio features which provide rhythmic descriptions as well as general spectral statistics. These features are extracted for all 6 segment seconds of a video, for all videos. Audio similarity is then calculated based on the nearest neighbor approach using Euclidean distance. So here we select a short sequence of the explosion, and what we retrieve is a list of videos where a similar sounding sequence can be identified in the video. And the cursor of the demo instantaneously jumps to the relevant position, so you can press the play button and compare the results. And as you can see, the demo identifies some duplicates, but also videos which have been captured from different perspectives. Here is another example from the Dallas protest shooting in 2016. This was an attack with firearms, so we first used the audio event detector to filter videos with gunshots. In the first video the sniper could not be identified, so we used the sequence of gunshot to look for similar sounding sequences in other videos to get videos that have been captured from different perspectives. And here we can see the results of the query. All these videos have the same audio signature, which means you can hear the same sequence of gunshots. So the advantage of this approach is that it clusters videos with similar acoustic scenery together. And because the scenery changes in relation to the different audio sources in an urban environment, videos which have the same audio scenery must have been taken in near proximity. So what you get from audio similarity search is an instant localization without GPS coordinates. The third audio model is audio-based video synchronization. The task is to synchronize various video files with unreliable time metadata. And this is solved by using the audio signature to relatively align these video files. The technology we use is based on noise invariant audio fingerprints. These audio fingerprints are derived from audio landmarks, which are represented by high energy audio peaks. Each audio fingerprint is an unambiguous hash value of 2 local frequent peaks with their offsets. Audio files are then synchronized by matching these hash values and estimating the offsets between them. And the higher the frequency of the matched values, the higher the confidence of the audio synchronization. Finally, we provide a video analysis module for the detection of different objects. The model is based on the YOLO architecture and is implemented in our Connected Vision framework, which is a modular, service-oriented, distributed and scalable computer vision platform. In the projects Florida and Victoria, we developed a large-scale platform for forensic analytics in massive video content. So in principle we have this massive video data provided by CCTV cameras or by mobile phone uploads. This video data is processed by the scalable platform, which is a heterogeneous system consisting of GPU clusters and CPU clusters. Detection models for visual, object detection and audio event detection are posted on the GPU platform. Detection results are then fed back into a database. This database is connected to a user interface. The backend of the demonstrator is based on the conduit platform. Processing pipelines are defined as directed acyclic graphs. In the backend we can monitor the processing log or observe the general status in the administration dashboard. The conclusions are: audio models facilitate a rapid start into an investigation. Audio event detection acts as a filter. Audio similarity facilitates comprehensive search. Visual models facilitate a broad search for certain objects, for example to follow hints by eyewitnesses. Another conclusion out of the project is that Hadoop is not the best choice for multimedia processes. We recommend platforms based on directed acyclic graphs. And the integration of audio algorithms into pre-existing visual analytics systems holds pitfalls. This was the presentation of our paper and the corresponding demonstrator. If you have any questions, please refer to the comment section or write us an email. Thank you very much.